Classical Physics Tutoring, Chapter 4, Section 3, Entropy. So we talk about entropy in this video. Now, where does entropy come from? In the beginning, during the Industrial Revolution, the steam engine was invented, and in order to consider the efficiency of steam engine, thermodynamics was developed. And during the process, the one particular engineering issue drew a lot of attention. The thermal engineering that time considers you have the heat source, which is the vapor, is fed to the machine. Okay, and the machine performs some work, and it's go back to heat source to repeat this work. So, like when you have V and P, this machine work like when get the heat, then suddenly expand and cool down. So at T1 and T2, and after that it's cool off and shrink. Then another vapor is injected. So it's received energy Q, right? And the remaining Q1 and the remaining is Q2 energy. And we already introduced Avogadro law, P1 V1 P2 V2 equals constant T1 T2. So this is the ideal gas, and if you use the ideal gas, this process is perfect. It's 100% efficient, because whatever the energy is provided perform the work, and remaining energy is going to be returned and new energy is added. It just repeated this process. Now, the problem is during this process some heat is lost. So this is the ideal gas process. If heat is lost, then this deviate from this ideal gas equation. So the PV is a heat energy, Q over T is a key. If this is constant in the process, then 100% efficient. So the Crosses introduced this equation. If this equation hold equal, then there's no loss of the heat. If there is a heat loss, then this process is going to be inequality. Okay, so in the ideal gas, you can move this state to this state without losing any heat, because if you expand and shrink, the entire energy is preserved. So from efficiency, the new concept is derived called reversible. If process is reversible, 100% efficient. If process is not reversible, irreversible, then it's no longer 100% efficient. Okay, that is very interesting. Now, if this is the continuous process, we use the integral from state Q1 to Q2. We take the change of entropy in this way. Okay, so the entropy was introduced as efficiency and reversibility concept, right? And for example, a gas volume V1 expand to V2, then the heat energy is taken, and entropy is going to be log V2 V1. So we have a concrete value. Another example is the temperature of the heat. High temperature gives the heat to low temperature. So entropy is going to be it's going to be the positive value. So the entropy had more meaning in the Carnot machine. It was efficiency, but reversibility concept came in because entropy does seem like it shows some thermal process characteristic. For example, higher heat, the heat energy flow to the lower temperature, then entropy is positive. That means after the heat transfer, entropy increase. And so they seem like a natural process. Naturally it's happened. This is not reversible. The temperature never go from low temperature to high temperature. And scientists say why? And seem like we can explain. The entropy has to increase. So every natural process, the thermal process, they examine, and not reversible when entropy increase. Okay, and this is a natural process. The big example came in when two different gases mix, diffusion. So you have a room and two different gases separated, and you open up. What's happened? The gas diffused, right? Why? This natural process. There's no reason, because the entire energy is the same, and the natural state goes to the directed by the energy power. For example, the water become round because that shape has the minimum energy, right? Okay, so but this diffusion is not driven by the energy, something else. So what is it? So this is not a reversible process. Once it's diffused, the nature doesn't separate the gas into two different and contain one type here and another type here. It's irreversible. So we suspect that entropy must increase in this process. So if you have the energy and kinetic energy here over T as entropy, it's a general definition of entropy. Entropy become like this, right? This equation we use for weight m. This is the moles, and this is the mole weight. So this is total weight. So we get this equation for entropy. That's the generalized entropy equation. Now, we had a gas S1 and S2, and total was S1 plus S2. Now, when you mix, we have this S prime entropy, right? And you look at S prime minus S1, S2, here you go, positive. So diffusion process, why diffusion happen? There's no law to explain this. The Newton doesn't tell you, Einstein doesn't tell you. No physics law tells you why diffusion happen. Okay? Now seems like we discovered a new natural law. It's called entropy increases. So entropy increases become one natural law, and that's the thermodynamics second law, right? The first one is energy conservation. Second is entropy increases. And this entropy increases imply a lot of things. So why reversibility is expressed by entropy? The entropy increase is second law of thermodynamics. That explains a lot of natural phenomena. It's like when this example used so many times, the egg fall on the floor and spatter, right? And this is not, it happened in nature, but egg never unspatter, right? Once it's break spatter, then you have to spend great effort and energy to put it back, and that's almost impossible. This irreversibility, and there are a lot of irreversibility in nature, and that seems to be explained by the second law. So that's became very important second law of thermodynamics. Entropy increases. Okay, entropy can decrease by adding energy. Okay, and I explained that to you in the next Gibbs entropy. Now Gibbs digging more the deeper on this issue. Say when you diffuse, you have a type 1, type 2 gas here, and they mix, right? Suppose it's reached to the equilibrium, right? And it's completely mixed. Now you put a little demon here, and the gas molecules flying around, and demon said, hey, this gas is type 1, so open the window. It's getting here. When type 2 gas come to the window, the demon opened that window again. So by repeating this process, this demon can separate type 1 and type 2 gas completely into two different chambers. And this demon does very tiny work, open window or close. Okay, is it negligible? Well, this argument, this demon's work is a major issue, because you know how many molecules we're talking about. Avogadro's number is 10 to the 23. No matter how small the work to open close window times multiplied by this is going to be decent amount of energy. And that means entropy can be reduced if energy is spent. Okay, so entropy increase, we're talking about thermally isolated system. Means there's no energy coming from outside. In this case, entropy always increase within this, and that's the thermodynamics second law. Okay, so how about Earth? The Earth entropy increase, but it's getting energy from sun. And what does it do? Entropy, the sunlight is going to grow plants, and the energy give up the energy given to the plant is going to collect all the minerals and compose the molecules, organic molecules, and this process is decreasing entropy. Okay, but it get fire and destroyed everything and scatter this again. That's increase entropy again. So entire Earth have some energy from sun, so it's someplace entropy decrease, overall entropy increase. So we don't know plus minus which way, but if you look at the entire universe is not getting any more energy from anywhere. In that case, entire universe is going to increase entropy. And some people suspect maybe that's defined the time. The time has a one way. It's always flow from past to future. Why? It never flow from future to past. I think this is something to do with increasing entropy, but this is just a philosophical discussion. There's no science in that argument. Now, if you look at this problem, amount of entropy increase is R log 2n, and this happened to be that this molecule used to be confined here, but suddenly have a choice of being here or here, a choice of 2, and number of molecules n, so molecules choice to be somewhere increased by 2 to the n. Okay, we call that microstate. So we can do thought experiment. Suppose we have a room all divided into the number of molecules and each molecules in each chamber, right? And molecule doesn't have any option to go somewhere else. And this is just like a completely frozen state, right? So entropy is 0 in this state. And if you remove some of the wall, suddenly each molecule has choice of being here or here. Then suddenly you increase the number of choice. Okay, so we calculate this kind of state, microstate, and it happened to be that entropy match up very well with this microstate. So if you have a more microstate, that means each molecule can choose to be more location free. A democracy, right? Here, molecules completely free to be anywhere and multiplied by n molecules. That's the maximum entropy. So the microstate is maximum this time. if everything is divided into chamber and jail cell, every molecule is confined, then entropy is 0. So the definition from this equation that gives derived at K, Boltzmann constant. This is Boltzmann's constant here, right here, log microstate. And what does this mean? Microstate is entropy, and the entropy increase. So the nature change to increase the freedom of the molecule, more microstate. So go back to this example. When all the molecules collected by the plant roots and create a leaf and a branch, it's confining into the plants. So that's decreasing entropy. When it's burned down and all spread by wind all over, the microstate increased dramatically. So that's increasing entropy. It does seem like we can say how random the location of molecule is. So starting with efficiency in Carnot machine and crosses inequality equation said irreversibility. Now the concept of entropy evolved to microstate randomness. And right now this is a statistical consideration of entropy, just like we did statistical consideration of the gas thermodynamics. And the gas is basically, we use Newton considerations as flying particles, and we got the gas nature thermodynamics for the ideal gas. And this was done by gas only because other state of matter is very complicated and difficult. Gas is the easiest one, so we established this in the previous video. Now entropy is also interpreted at the micro level. Means in the micro level it's a log of number of microstate. That's the entropy. Okay, and this matches very well with the classical definition of entropy, which is Q1 to Q2. Okay, and this supports the thermodynamics law, second law, and the second law can be understood much better using this definition. This is Gibbs entropy. Now, since this came out, Boltzmann tried to improve the gas thermodynamics called H theory, and is somewhat successful, but make it long story short, he defined entropy using this, and this reflects some of these Gibbs entropies, but not quite. So it's like a partial success. And if you're interested in this, you can look it up and do this homework. Boltzmann's H theory. He tried to incorporate this entropy concept into the gas, because the statistical thermodynamics, the gas, that was okay, temperature, energy, everything was statistical average, right? But it didn't have any entropy, and that's what Boltzmann's H theory incorporated. So from the statistical average, entropy can be defined, but it didn't quite reflect the true meaning of entropy, which is the log of microstate. And microstate is usually exponential function. By having a log, entropy become the number that the scientist can handle, because without log it's just microstate is too large. Okay, so this is the whole story about entropy and the second law of thermodynamics. I hope you like it, and if you like, subscribe.